part 4, A4. How many more do I have left? All right, I'm only going to do A4 because B1 is extremely similar to a lot of the other things. Right, that's just simply energy conversion stuff. So, okay, A4, right? So this is another photoelectric effect problem. So what is the energy of an incident photon in joules, right? So what we're looking at here, right? The question's, talking about hitting something with ultraviolet light that has 300 nanometers of incident light on a sample of potassium metal. And so, what we have to calculate now is how much energy is actually in that 300 nanometer photon, right? That's hitting the thing. So the equation that we use is E. Is E is equal to hc over lambda. Right, so h is Planck's constant, so that's 6.626 times 10 to the negative 34 joule seconds times the speed of light, which is 2.9979 times 10 to the 8th meters per second over the wavelength, which in this case is 300 nanometers. And so nanometers and meters don't directly cancel out, so you have to convert that. So that's simply 1 times 10 to the negative 9 meters per nanometer. So we get meters canceling, nanometers canceling, and then seconds canceling. Right, and so now we can just plug all that stuff in. Right, so we have 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 300 times 10 to the negative 9. So that comes out to 6.621 times 10 to the negative 19 joules, right? Which I think is what I have on the answer key. Yeah, 6.62. Right, so that's the energy of the photon that we're hitting the potassium with. The work function of potassium is 2.29 electron volts. How much extra energy does the incident photon have beyond what is necessary to emit an electron in electron volts? So now what we have to do is just simply convert the energy of the photon into electron volts. And so that relationship is, 1 electron volt has the energy, is equivalent to 1.6218 times 10 to the negative 19 joules. So to do that conversion, right, we have 6.621 times 10 to the negative 19 joules times 1 electron volt over 1.60218 times 10 to the negative 19 joules. So, right, joules cancel, we'll only end up with electron volts. And so that comes out to 1.60218 divided by negative 19, or times 10 to the negative 19, is 4.133. I will just keep it the same amount, right? So 4.3 electron volts, right? So that's the energy of the photon in electron volts. So now, right, we can calculate how much extra energy there is by just simply, subtracting the two, right? So we have the difference in energy is going to be equal to 4.13 electron volts minus 2.29 electron volts. So that comes out to 4.13 minus 2.29, 1.84 electron volts, right? So that photon has 1.84 electron volts more energy than is required, right, to release an electron from the potassium metal. Without performing any calculations, if the wavelength of the incident photon is 430 nanometers, would you expect the amount of extra energy to increase? So as I've talked about, already in other sections of this, the higher the wavelength, the lower the energy, right? There's an inverse relationship between energy and wavelength, and so if you have, if you're comparing two different photons or two different sources of light, the one that has the lower wavelength is going to have the higher energy, right? The one that has the higher wavelength is going to have the lower energy, right? Because it has that inverse relationship, going back to, that equation right there where energy is equal to hc over lambda, right? So the larger that lambda is, right, because you're dividing by it, that's going to make E smaller, whereas because H and C both are constants, whereas the smaller that lambda is, right, that the larger E becomes in those cases. So in that case, right, it will decrease in energy. What is the maximum wavelength of incident electromagnetic radiation that will result in the photoelectric emission of electrons by a sample of potassium? So for this problem, what I'm really asking for is, what is the wavelength of 2.29 electron volts, right? Like what's that value? Because, right, we know that the work function is 2.29 electron volts for the potassium. That is the bare minimum amount of energy required to release, an electron from the potassium. And so we can calculate what the wavelength of that's going to be. So now, right, if we look at the equation that we have, right, so E is equal to HC over lambda, right, we can rearrange this so that we have lambda is equal to HC over E in this case. So, we can plug in everything that we have. So we have 6.626 times 10 to the negative 34 joules seconds times 2.9979 times 10 to the 8th meters per second over, right? And so right now we're at, in electron volts, so that's 2.29 electron volts. And so we want to make sure that, for everything to cancel out, the electron volts have to be converted into joules. So to do that, right, all we have to simply do is multiply this right here, right, by 1.60218 times 10 to the negative 19 joules per electron volt, right? Because now electron volts cancel, joules cancel, seconds cancel. So all we end up with is meters, right, which is what the the wavelength, the unit that it should be in. So the wavelength then is going to be equal to, so we'll just plug in all these numbers. So 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 2.29 times 1.60218 times 10 to the negative 19 gives us a wavelength of 5.41 times 10 to the negative 7 meters, right? And so we can just simply convert that into nanometers by multiplying by 1 times 10 to the 9th nanometers per meter. So the meters cancel. 1 times 10 to the 9th. So what we get is that the wavelength of light is 541 nanometers, right? And that's, I think, what I have in the key. Yes, right. So, right. So you have to have at least, a source of light that's giving at least 541 nanometers of light, right, to eject an electron from potassium, right? If it's, that wavelength of light is lower than that, then, you're going to eject the electrons as well, right? But you have to have at least 541 nanometers of light. Would increasing the intensity of light have any effect on the process? So not really, right? So I mean, it depends. So you have to hit, right? So the wavelength of your light has to be at least the required amount for the work function, right? So if you're at, we calculate, right, we're at 541, right? So if you're using 600 nanometer light and you're shining that on your potassium metal, it doesn't matter how bright you shine it. If the cutoff, all it's doing is giving you 600 nanometers of light, it's not going to release anything, right? So it very much depends on but if you're below 541, right, all you're doing by increasing the intensities, you're just hitting it with more photons then, right? And so if you're at the threshold in terms of the energy per photon when hitting it, right, that's then going to be enough energy for it to shoot off the electron. Now, one thing to think about too is that um, it's extremely difficult to truly get like monochromatic light, or at least have like a true cutoff of, light. So, when we're thinking about light, most light is actually pretty broad, right? And this is the most intense peak, and everything. But you can have still a small amount that maybe goes towards whatever your threshold that you have is. And so, if you're increasing the intensity, right, there's going to be more and more of this small region that'll probably start getting through as well. As you start using like lasers and various different tools, right, it's going to start like tightening up a lot. But again, right, there's still going to be a small amount of tail that might get through or something a lot in those cases. So you might be able to get some, but it's not going to be, you're really gonna have to go extremely intense in that case. And so, when we're talking about intensity, right, what we're really talking about is, how many joules are hitting it, but you have to have, right, the amount of energy really to release it, in those cases. So, yeah. I mean, intensity, all it does is, right, you're just simply increasing like how many photons you're really hitting the area with. And I think that's it.